You run a simple query. Select from users where email equals alice@example.com. The database thinks and thinks. 2.3 seconds later, it finally returns one row out of 10 million. Now you add an index. Create index on the email column. You run the exact same query. This time, 2 milliseconds, over 1,000 times faster. So what changed? What magical data structure did that index create that turned a crawl into an instant lookup? The answer is a B tree. And by the end of this video, you'll understand exactly how it works. Without an index, the database has no shortcut. It starts at the first row and checks the email column. Not a match. Move to the next row, not a match. Next row, still not a match. This is called a full table scan. The database reads every single row until it finds what it's looking for, or worse, until it reaches the end and confirms the row doesn't exist. With 100 rows, this is fine. With 1,000 rows, it's tolerable, but with 10 million rows, that's 10 million comparisons. And as your table grows, the query gets linearly slower. This is O of n. Every row you add makes every search a little bit worse. Here's a natural idea. What if we sorted the data? With sorted data, we could use binary search. Start in the middle. Is our target bigger or smaller? Eliminate half the possibilities. Repeat. Binary search finds any element in O of log n time. For 10 million rows, that's just 23 comparisons instead of 10 million. Incredible. But there's a problem. Databases aren't read-only. Every time someone inserts a new row, we'd have to shift elements to maintain the sorted order. That's O of n for every single insert. We need something smarter. A data structure that stays sorted, supports fast searches, and handles insertions gracefully. That data structure is the B tree. A B tree looks different from the binary trees you might know. Instead of each node holding one key with 2 children, a B tree node holds multiple keys and has multiple children. Here's a B tree of order 4. That means each node can hold up to 3 keys. The keys within each node are always sorted from left to right. At the top is the root node. Below it are internal nodes, and at the very bottom are the leaf nodes. Every leaf sits at the same depth. The tree is always perfectly balanced. The keys act as dividers. If a node holds the keys 10, 20, and 30, then all values less than 10 are in the first child. Values between 10 and 20 are in the second child, and so on. This is what gives the B tree its power. Each node is a multi-way decision point. Let's search for the value 42. We start at the root node. The root holds the keys 20 and 50. 42 is greater than 20 but less than 50, so we follow the middle pointer down to the next level. Now we're at an internal node with the keys 30 and 45. 42 is greater than 30 but less than 45. We follow the middle pointer again. We arrive at a leaf node. We scan its keys. 35, 40, 42. Found it. 3 levels. 3 comparisons. Out of potentially millions of keys, we found our target by visiting just 3 nodes. That's O of log n, just like binary search. But as we'll see, the B tree has a crucial advantage that binary search trees don't. Inserting into a B tree always starts at a leaf node. First, we search to find the correct leaf. Then we insert the new key in sorted position. But what happens when a leaf node is already full? Let's say we're inserting 25 into a node that already holds 20, 23, and 28. 4 keys in a node that only allows 3. The node splits. Here's how. We take the middle key, 23, and promote it up to the parent node. The remaining keys divide into 2 new leaf nodes. One gets 20, the other gets 25 and 28. What if the parent node is also full? It splits too. The split cascades upward, and if it reaches the root and the root splits, a brand new root is created. This is the only way a B tree grows taller, and that's what keeps it perfectly balanced. Here's the real genius of B trees, and it has nothing to do with algorithms. It's about hardware. A CPU cache access takes about 1 nanosecond. Reading from RAM takes about 100 nanoseconds, but reading from a disk, 10 million nanoseconds. Disk access is literally 10 million times slower than the cache. Now, every time we visit a tree node, that's 1 disk read. A binary search tree with 10 million keys has about 23 levels, 23 disk reads. But a B tree node is designed to fill an entire disk page, usually 4 kilobytes. That's enough room for hundreds of keys in a single node. With 500 keys per node, a B tree holding 10 million records only needs 3 or 4 levels. 3 disk reads instead of 23. The B-tree's wide, shallow shape isn't just elegant. It's engineered to minimize the most expensive operation a database can perform. There's one more twist. Most databases don't actually use plain B-trees. They use a variant called the B+ tree. In a regular B-tree, data can live in any node, internal or leaf. In a B+ tree, all the actual data lives only in the leaf nodes. Internal nodes are purely for routing. They hold keys and pointers, nothing else. Why does this matter? 2 reasons. First, since internal nodes don't store data, they can fit more keys. More keys per node means an even wider, shallower tree, even fewer disk reads. Second, and this is the clever part, the leaf nodes are linked together in a chain. This makes range queries incredibly fast. Need all users with IDs between 100 and 200. Find 100 in the tree, then just walk along the leaf chain. No need to traverse back up and down the tree. So where do you actually encounter B+ trees? Everywhere. PostgreSQL, MySQL, and SQLite all use B+ trees as their default index structure. When you write create index on a table, you're building a B+ tree behind the scenes. The database takes the indexed column values, sorts them, and organizes them into this tree structure. Composite indexes are especially interesting. Create index on last name and first name together. The B+ tree sorts first by last name, then by first name within ties, like a phone book. This means the index helps queries that filter by last name or by last name and first name together. But it can't help a query that only filters by first name because first name isn't the leftmost column. This is called the leftmost prefix rule. Now that you understand B-trees, here are some practical takeaways. First, indexes aren't free. Every index is a separate B+ tree that must be updated on every insert, update, and delete. Too many indexes slow down your writes. Second, index the columns you frequently search, filter, or join on. If your queries often include a where clause on a column, that column is a good candidate for an index. Third, watch out for low cardinality columns. Indexing a Boolean column like is active with only 2 possible values rarely helps. The database might just scan the whole table anyway. And finally, remember that the query planner decides whether to use your index. For very small tables, a full scan can actually be faster than traversing a tree. Now, when you see an index speed up a query from seconds to milliseconds, you know exactly what's happening under the hood. A B-tree is doing what it was born to do.